For 1-5, we are going to be talking about square roots. Your target is I can evaluate expressions containing square roots and classify numbers within the real number system. Okay, so first we're going to talk about a couple of definitions. The definition of a square root is a number multiplied by itself to form a product is the square root of that product. Square root is essentially an operation. It looks like that. And I always ask myself, what times itself is under the square root? A perfect square is a number whose positive square root is a whole number. So for instance, 2 times 2 equals 4. So 4 is a perfect square. 3 times 3 equals 9. 9 is a perfect square. 4 times 4 equals 16. That's a perfect square. So we're going to go ahead and look at this chart, and we're going to write the first 10 square roots, square numbers and their square roots. So our first one is, well, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. And you could keep going on. Now the positive square root, it's literally positive square root of 1. You think, what times itself is 1? Well, it's 1. The positive square root of 4, what times itself is 4? 2, because 2 times 2 is 4. The square root of 9 is 3, because 3 times 3 is 9. The square root of 16 equals 4. 4 times 4 is 16. The square root of 25 equals 5. And I'm sure you can notice the pattern, because we're going first 10. The square root of 36 equals 6. The square root of 49, I bet you guessed it, it's 7. The square root of 81 equals 9. Oh, we skipped 64. We'll scoot that one down. The square root of 64 is 8. The square root of 81 is 9. And the square root of 100 equals 10. Now this next column is called the negative square root. So literally it's taking a negative times a square root. So essentially it's negative 1 times the square root of 1. You first take the square root of 1 is 1. So it'd be negative 1 times 1, which is negative 1. Negative the square root of 4 would be negative 1 times 2, which is negative 2. Negative the square root of 9 would be negative 1 times 3, which is negative 3. And I'm sure you recognize the pattern. Notice the negative is outside the square root. That's very, very, very important. Negative the square root of 16. Now let's follow the pattern. It's going to be negative 4. Negative square root of 25 is negative 5. Negative the square root of 36, you got it, negative 6. Negative the square root of 49, negative 7. Negative the square root of 64 is negative 8. Negative the square root of 81 is negative 9. And last but not least, negative the square root of 100 is negative 10. Now, I just said it's so important that this negative is on the outside. Well, what happens if it's on the inside, like the square root of -4? Well, if you ask yourself, what times itself is -4, you might think, oh, -2. Well, let's think about it. -2 times -2 is a +4. That can't work. 2 times negative, well, that's not the same number. They're not itself. So that can't happen. You can't take the square root of a negative number. Can't do it. I always think this is really fun when we're estimating the square root to the nearest 10. Notice 42 is not a perfect square. So I do it in a couple of steps. If I'm taking the square root of 42, the first step I do is I pick this perfect square above and below. So I'm going to look back at my chart, and 42 would fall right about here. So it's between 36 and 49. So I'm going to write the square root of 36, the square root of 49. The second thing I'm going to do is take the two perfect square roots. So I know it has to be between 6 and 7. Any number between 6 and 7 is going to be 6 in some sort of fraction. But how far? So what I'm going to do is I'm going to see how far is it from perfect square 1 to perfect square 2. And I'm going to use this number line to help me. So let me just move the number line over here so we can have a little bit more room. And I'm going to take a look and say 42 is right here. 41, 40, 39, 38, 37, 36 is right here. 42, 43, 44, 45, 46, 47, 48. We'll just extend it a little bit, and 49. So I want to see if the perfect square to perfect square is how many spaces. So I'm going to count. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's 14 spaces from perfect square to perfect square. Then I'm going to look, well, did I go the whole 14? No, because if I went 14 out of 14 spaces, that'd be 1, and I'd be at 6 plus 1, which is 7. And that's not right. I didn't go all 14 to 42. I only went 1, 2, 3, 4, 5, 6 out of the 14 spaces. So 6 and 6 out of the 14 spaces from perfect square to perfect square. Now you can do some long division, and you could do I apologize, when I counted one wrong. It's actually only 13 spaces. 13, 13. Make sure you're being careful. And the way that I checked myself, as I said, 49 minus 36 equals 13. So that was another way instead of counting the spaces, because sometimes counting them there, you can miss one or add one where you don't need to. Well, I thought to myself, because I'm estimating, I said, on the side, I said 6/13 is approximately 6/12, which equals 1/2, which is 0.5. So I could say it's about 6.5. Now, I want you to try this one. Try with your desk partner, decide which is bigger, 7 or the square root of 52. Well, I know that 7 is the number 7, and I thought, well, the square root of 52 is between the square root of 49 and the square root of 64. So I know the square root of 49 is 7, the square root of 64 is 8, so I know it has to be 7 point something. Well, is 7 or 7 point something bigger? Oh, 7 point something is, so I know what is bigger, the square root of 52. Okay, so take a minute and we're going to jot these down. So the real number system, they have some special names. The first one we're going to talk about is real numbers. It's everything on the number line. Natural numbers are abbreviated with an N. Real numbers are abbreviated with an R, a fancy looking R, or your counting numbers. Think of 1, whoa, 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 2, oh, 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 3, oh, oh, oh. What am I thinking of? Sesame Street and the couch. Those are your natural numbers. Whole numbers are a W, and now we have 0. The way I remember it is whole has a 0 in it. So it starts at 0, 1, 2, 3, dot, dot, dot. It's almost like your number line's growing. So we started here with our number line, and we had 1, 2, 3, so on and so forth. And then our number line grew, and we got 0, 1, 2, 3, 4, so on and so forth. And then we have integers, which integers have an interesting abbreviation. It's a Z. Now, well, what do you think will be the next part? We have negative numbers. So I'm going to put dot, dot, dots on the left. -2, -1, 0, 1, 2, dot, dot, dot. So our number line grew again. So we have -2, -1, 0, 1, 2, 3. Then we have rational numbers. Now, rational numbers have subcategories. Rational numbers have an interesting thing, too. They're cute. It's any number that can be written as a fraction. Notice every single one of these numbers, like 2 is technically 2 over 1. 1/3, -2/5. If it is a rational, it is either a terminating decimal. These are all terminating decimals because they're 0.0. Or you can have 1/2, which is 0.5, or a repeating decimal. So 1/3 is 0.3 repeating. Then you have irrational numbers, which are numbers that are non-terminating and non-repeating decimals. Things like pi. Anytime you have the square root that's not a perfect square. So for instance, the square root of 33, that's not a perfect square. So I have a little way, some little things that we can remember them. There's this box here. And on the smallest part, the most small part of your number line, you have your natural numbers. And that's your 1, 2, 3, so on and so forth. Then next you have your whole numbers. It got a little bigger, you added 0 in there. Then our circle grew even bigger. Think about as you learned, you first learned about counting numbers, and then you learned about 0, and then you learned about negative numbers. 0, 1, 2, dot, 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 dot. Then, all of a sudden, you know about rational numbers. And in rational, you have your terminating and your repeating decimals. So that's 1/3, 2/5, 6 over 7, so on and so forth. Then we have over here, I like to call it irrational island. Irrational island. Because if it's irrational, it stands alone. It has no other names associated with it. You might have the square root of 13, pi, the square root of 52, so on and so forth. Now, when you have these directions to classify, I always look, what's the smallest circle it fits in? So number 1 is 5. The smallest circle that it fits in, I'm going to go in and say, oh, it would fit in the natural. And then you work your way out. If it's natural, it was also whole, it was also an integer, and it was rational. Then I have to decide, well, if it's rational, it's either terminating or repeating. It's terminating because it's 5.0. It's a terminating decimal. Let's look at number 2, 0.1, 1, 2, 1, 2, 1, 2, 3, 1, 2, 3, 4. It does not repeat. If it doesn't repeat, it would be over here in irrational island. Well, irrational island's only irrational. Number 3 says 4/5. 4/5 is really 0.8. Does it fit? Oh, the smallest circle it fits in is actually rational. So I just know that it's rational. And since it's 0.8 is a terminating decimal. Real quick, just think if you had -3, you would start with integer and work your way out. And I would say that would be Z for integer, rational, and terminating.